Hello everyone. Today I'm going to talk about methods of data valuation for machine learning. This presentation is based on two recent 2019 and 2020 ICML papers, and most of the work is done by James Zhu and me at Stanford University. So let's start with a very simple example. Let's say you have an AI for health company, and your job is to detect melanoma. So given images of skin, you want to see if there is a melanoma lesion in it or it's a benign lesion. You have a small initial data set, you train a model on it, and you get a 60% prediction accuracy. Well, that's not a very good performance, so you want to increase the size of your data set. You go and negotiate with a hospital, get some of their data, and add that to your initial data set. And you see that your performance improves to around 80%. So that's a huge improvement. Now the question is how much you should pay to the hospital to compensate this increase. In other words, how much of this papers, and most of the work is done by James Zhu and me at Stanford University. So let's start with a very simple example. Let's say you have an AI for health company, and your job is to detect melanoma. So given images of skin, you want to see if there is a melanoma lesion in it or it's a benign lesion. You have a small initial data set, you train a model on it, and you get a 60% prediction accuracy. Well, that's not a very good performance, so you want to increase the size of your data set. You go and negotiate with a hospital, get some of their data, and add that to your initial data set. And you see that your performance improves to around 80%. So that's a huge improvement. Now the question is how much you should pay to the hospital to compensate this increase. In other words, how much of this 20% improvement, how much of this 80% performance can be attributed to the hospital data? Well, taking a step back, let's talk about data valuation and why it is important in machine learning. There are three main groups of people who work with data. You have machine learning engineers and scientists. You have data vendors, and you have individuals. So machine learning scientists care about data valuation because usually their data sets come from different sources. So data valuation will help them to find the data sources that have the highest quality and acquire more. Data vendors buy and sell data. So that's the question of what price they should buy and sell their data. An individual, everyday people who go on the internet, Facebook, Instagram, their data is being used for advertisement and many other applications to generate revenue. And given the current setting that the governor of California, the Senate of the United States, and the European Union have asked tech companies to compensate people for their data, individuals also start caring about data valuation. Now, let's think about machine learning. Any machine learning problem can be divided into three main components. You start with the training data. We have shown it here with three simple symbols. Let's assume they are data samples or just data sources: star, pentagon, and hexagon. Then you have a learning algorithm. So learning algorithm is basically a black box that takes the training data and outputs a trained model. So anything such as your model class, let's say you're using random forest or you're using deep networks, plus hyperparameter selection, plus random seed selection, blah, 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 all of this could be integrated as the learning algorithm black box. And given these two steps, so training data and then training a model using your learning algorithm, you have a trained model which has some performance given your chosen performance metric, whether it's F1 score, accuracy, or mean squared error. So in our case, we're talking about test accuracy, and the performance score is 0.8. Our desired data valuation scheme wants to divide this final performance metric among the initial data points. So let's say the Pentagon data set was very valuable. The Pentagon data point was very valuable with like 0.4 valuation, but the star was not that valuable, so it got 0.05. Now, if you think about this problem, the value depends on 3 ingredients. Your fixed training data set. So when we're talking about data valuation, at least for now, you have a fixed training data set and you want to find the value of the data points in that data set. You have a fixed learning algorithm, and then you have a fixed performance metric. Given these 3 ingredients, these 3 fixed ingredients, one can think of many ways of data valuation, but we want the right one. So let's look at one of the examples. Leave-on-out method is a very famous method in machine learning and statistics. So as an example, let's look at our simple example that we had. Let's say we want to find the value of data point star. As we said, when you train a model on the 3 data points you have, you get 0.8 performance. Now we remove data point star, we act as if it didn't exist, and we see the performance drops by 3%. We can say now that the value of data point star, the leave-one-out value of data point star, is 3%. The question is this valuation method reasonable? And the answer is going to be no, but why? To define reasonable, we have to first define our desirable properties of data valuation. The first property is very intuitive. It's called null element. We want a useless data point to get no value. And the way we can define useless, the most comprehensive way to define useless, is that if we add it to any subset of training data. So as we said, you have the fixed training data set. You take data point star and you add it to any subset of your training data, and you see that the performance does not change. So having or not having this data point never changes anything. This data point should get 0 value. The next condition is more of a fairness condition. So let's say you have 2 data points that are interchangeable. And the way we define interchangeable is, again, in the most comprehensive manner. So if you add either of these 2 data points to any subset of your training data, the improvement in performance is always the same. And the last one is linearity. Let's say your performance metric, as we said, we have 3 main components: training data, learning algorithm, and performance metric. Let's say your performance metric is a linear combination of individual performance metrics. You want this linearity to be preserved in data valuation. So the simplest case of having linearity for performance metric is the test accuracy itself. Test accuracy is usually just the summation of 0-1 accuracy on individual test data points. We want this linearity to be preserved in the value we assign to our data points. So these 3 desired properties are literally Shapley axioms, which is a very well-known concept in game theory. And it can be proved that uniquely, the only value that satisfies these 3 properties is what we call data Shapley value. And this is the formula for it. So assume you have your fixed training data set and you are looking at data point K. So let's delve into this specific formula and see how it works. Assume S is just a random subset of your training data that does not contain K. Let's train a model on S and look at its performance. Then let's add data point K to the subset S and look how much the performance improved or got worse. This subtraction is literally the marginal contribution of data point K to that subset S. Now, for any given size of this subset S, we want to normalize this marginal contribution by the number of subsets of that size. Then we sum this marginal contribution over all possible subsets of your training data. So data valuation, the data Shapley value is nothing but a weighted average of marginal contributions of that data point. So this is computationally very hard to compute. It's exponential in the size of your training data set. But what we managed to do was to design Monte Carlo sampling methods and also heuristics that can efficiently compute this value. So let's look at the data Shapley value of data point star in our simple example. You have the 3 initial data points and your performance is 0.8. Okay, so let's look at subsets of size 2. Because if you remove data point star, you have only 2 data points remaining. So there is one of these subsets. So we look at the marginal contribution of data point star to the only existing subset of size 2, and as we said before, it's 0.3. There are two subsets of size 1, so you can either have the pentagon by itself or the hexagon by itself. We look at the marginal contribution of data point star, but this time we divide the marginal contributions by 2, because we have two subsets of size 1. Then we look at subsets of size 0, so just having data point star versus not having any data points at all. The summation of these weighted average of marginal contributions is the data Shapley value of data point star. And if we repeat this data valuation for all of the data points in the training data set, these values are going to satisfy three data Shapley properties, the three Shapley axioms. So the notion of Shapley value was developed by Lloyd Shapley, a famous figure in economics. And it's for cooperative games. So just think as a cooperative game as having a set of players, here shown by soldiers, where when they cooperate together, they'll get a specific reward. Let's say you and your 5 friends, if you cooperate together, you get reward X. But for any possible subset of you that also cooperates with each other, so let's say 2 of their friends just disagree to cooperate. For every possible subset, we can assign a different reward. The Shapley value, what it does is that for the case where all of you cooperate and get a reward, it can compute how much of that reward each of the players is going to get. And if you think about machine learning, it's nothing but a cooperative game between data points. So you have a bunch of data points as players coming together, cooperating to train a model, and then getting a reward, which is the performance of that model. Let's say the test accuracy of that model. So the 1 million ImageNet images come together as 1 million players. They cooperate with each other, and they get the reward, which is, let's say, 87% top 1 accuracy. But for any possible subset of those players, we can still find the prediction accuracy. So let's say I remove half the ImageNet data points. I still have 500,000 images, and I still can train a model on it. And I can see the performance of that model. So as we said, the data points value is its expected, a weighted expected contribution to the performance of the model. And well, we have now a data valuation scheme, and it satisfies the properties that we desired. But are there any other use cases for it? Again, as we said, the data points value is a marginal is a weighted average of its marginal contribution to all possible subsets of the data set. Okay, so let's say you have a high value data point. What it means that going back to our formula, you have this data point k that gets a very high value. It means that usually when you add it to a random subset of your training set, it increases the performance significantly, meaning that it's a very good data point. So a high value data point is usually adding significant information. So we expect it to be a very clean data point, correctly labeled inside the correct distribution. But at the same time, a low value data. So think about a data point that gets negative value in this formula, all right? So you have data point k, whose value is negative, meaning that this denominator is usually negative because the denominator is always positive. It means that if you have a subset of your data S, you're better off not having data point k than just having it, because adding data point k reduces performance. All right, so we expect this data point of low value to be harmful to the training task. So it can be a noisy data point, it can be an outlier, it can be a mislabeled data point, or in general, a data point that usually hurts performance given your learning algorithm. Okay, so naturally, the first application of data Shapley would be to identify low quality data. All right, so let's say we have a spam classification model. We use naive-Bayes because it's very famous for the task of spam classification. So we take our original training data set and randomly change the label of 20% of our initial training set. So we make the label incorrect. So we have, let's say, 10,000 data points. We take 2,000 of them randomly, and label the ones that are spam as not spam and vice versa. Now, the task is to go over this data set that has noisy labels and just fix the samples that are mislabeled, like manually. If you inspect this data set randomly, you can expect that you should look at all the data points to be able to fix all of the labels. So you can see that the number of incorrect labels that are fixed is linear in the size of the data set you inspect. Now, if you do this with leave one out, you can see it's not much better than random. But let's do the other way. Let's take our data set and let's compute the data Shapley values of every data point in that data set. As you can see, this time we can rank the data points based on their value. And as we expected, data points that are bad, that are mislabeled, are going to get low value because they are the ones that usually hurt performance. So if we start inspecting data points from the least valuable to the most valuable, we expect that most of the mislabeled data points are among the least valuable. And as you can see here, when we inspect 20% of data points that get the least value, more than 90% of data points that were mislabeled are discovered. All right, so let's go the other way around. Let's identify the most important data points. So as we said, when a data point gets very positive value, it means that it's usually helping a lot. It's a very important, crucial data point. All right, so let's look at this data set. It's a very famous data set called UK Biobank. It is a very comprehensive data set of phenotype and genotype information of 500,000 individuals in the United Kingdom. And these patients, these individuals, the data is gathered in 22 different centers in the UK. So they are distributed across the country. What we do is that we create binary disease prediction data sets. What it means is that in the UK Biobank data set, we have the information of the patients and we know which of them will get a specific disease, let's say breast cancer, prostate cancer, etc. Now, we want to train a model to predict if a specific patient, given his or her features, is going to be identified with this specific disease. As we said, the data Shapley framework can work on individual data sets, but at the same time, if you look at the formula, it can work on sources of data. So this time, instead of finding data Shapley value for individual one of these 500,000 people, we find data value for the individual 22 centers. Now, let's look at what we find out. So this is the map of the UK, and you have your 22 centers. So the green bar basically shows the population of each center. So how much each center contributed to the data set. So let's say center 3 and center 14 were the ones that had lots of patients, but let's say center 15 was very small. So our first task is breast cancer detection. So predicting whether a patient will get breast cancer in the future or not. And then we find the data Shapley value of the 22 centers. As you can see, for the specific disease, the value is very correlated with population. So let's say center 14, that is a very large center, is contributing most of the data points. So it's reasonable that it gets most of the value too. But that's not always the case. So let's look at colon cancer. As you can see, the value of centers is very unrelated to the size of the centers. So it's not necessarily the case that the data source that gives the most number of data points is the one that's going to be most helpful with your task. So let's look at center 15, for instance, because center 15 has contributed a lot of patients to the data set. It's a rather large center, but it gets a very negative value. So the question is, what's wrong with this center? What can be changed with this center? Like, why does this center get low value? Is it the case that the data points are mislabeled or you have wrong features? Probably that's not the case. What is the case is that when you train a prediction model to predict colon cancer from a patient's genotype and phenotype data, the feature age comes as the most predictive feature. So the older you are, the more probable it is that you're going to get colon cancer. This specific center has this feature where getting colon cancer is unrelated to age. So when we say a data point gets low value, it's not always the case that it's a very bad data point. It can be the case that it just follows different rules from the overall trend of the data set. Now, let's forget about centers and this time go and find the data Shapley value of individual patients, of individual data points. So let's say we have our individual data points and we get some performance, let's say 68% test accuracy. If we start removing data points from our training set, we expect the performance to drop because you're just making the training set smaller. And this is what's happening. So if I remove 40% of the data points in my training set, I can see that the performance drops from around 68% to around 65%, which is reasonable. Now, if you start removing data points from the most data Shapley value, so find the data Shapley value of your individual patients and start removing the ones that have the highest value, you can see that the performance drops very sharply. And as you can see in the plot, after removing around 40% of the data points, the performance drops to 50%, which is basically random prediction. So you still have the majority of your data points in your training set, but the prediction doesn't work anymore. You cannot train a model to predict breast cancer. There's no useful information, at least given your learning algorithm, in that remaining patients for predicting breast cancer. Now, the most interesting thing is that you can go the other way around. So you can start removing data points to get the least value. And as you can see, after removing around 30% of data points that get the least value, your performance improves drastically. So you're having 30% less data points. Your data set has become smaller, but your performance has improved. And just to make sure things are correct, when we say performance, we're talking about performance on a held out set. So we have three parts of data. We have the training set, which we compute the value for. We have a valuation set, we have a validation set, or let's say test set, where we use as our performance metric to compute the value. Then we have this third set, this third unseen held out set, which we are reporting the results for. And after the first data Shapley work, this has actually found applications in widespread areas. So I just saw this ACL paper this year, this natural language processing paper, where given a data set for a specific task, which was automatic dialogue evaluation, the authors, what they did was they computed Shapley value for the training data points and removed the ones that had very small value. And as you can see, they kind of totally beat the benchmark for this specific task. So again, they are removing data. They're making their training data set smaller, but their performance is actually increasing. And the very last application that I'm going to be talking about is domain adaptation. And let's see what is the intuition behind that. So what is domain adaptation? It's basically this case. The setting is still the same machine learning setting. You have a training data set, you have a learning algorithm, and you have your performance metric. The only difference is that the distribution between these two is slightly different. So usually you have a training data set and your test data, which you find a performance on, comes from the exact same distribution. But when you're talking about domain adaptation, you have a training data, but your target data, which you care about, is actually different. So let's say one simple example is that you have like automobile driving data in the morning, like in sunlight, but what you care about is the performance of your autonomous vehicle at night. So almost nothing has changed. We still have the three ingredients. We have a training data, we have a learning algorithm, and we have a performance metric. It's just that the test data distribution is different from training data, but nothing has changed for the data Shapley framework. Now, one can think that if we find the value of data points in the training data, with respect to the performance metric that comes from the test data, we can find the data points in the training data that help the most with the test data, and vice versa. So what's the approach? Let's compute the data Shapley value for our training data points, given a small subset of data that comes from the same distribution of test data. Then remove the ones that have negative value, because they are the ones that are usually contributing negatively to performance. Then let's reweight the rest of the data points with their relative value. So let's say data point Pentagon gets a very high value. We want it to have more impact on the model trained for prediction on the test set. So the first example is a very useful case. It can happen in real world a lot. So the task is, as we talked about in the beginning of the presentation, is melanoma, is detecting skin lesions out of 7 different classes, one of them being melanoma. The target data that you care about are clinical examples. So these are images that are taken by dermatologists using a very specific device called dermoscope or dermatoscope that normalizes the lighting condition, etc., etc. So they are very hard to acquire. And also they're labeled by dermatologists. So your target data is actually a very expensive data set that is hard to acquire. So the best way to get a very good performance on your target data is to go and gather a training data set that looks like it. But it's very expensive. Now, what we did is that we used Google image search. I personally used Google image search to create a training data, a very cheap training data that was created in around 4 hours by searching the name of these diseases with the specific keywords. Now, because this data set is very cheap, and as you can see, it is very inaccurate, so you have images that are very unrelated to your target data. When you train a model on this training data, the performance on the target data is very small. But let's do as we said. So let's compute. Let's say we have 10,000 data points from this HMA 10,000. We use 100 of those to compute the value of data points in our training data. So let's say you have enough money to acquire 100 data points that are similar to your test data. You compute the data Shapley value of individual images in this very cheap data set. We remove the ones with negative value and reweight the ones with positive value. As you can see, test accuracy on a 7-class classification task improves from 29.6% to around 38%. So it's a 25% increase in performance without any expense or any let's say measurable expense, any monetary expense, because you didn't buy any data, you didn't use any annotators to label your data. It is just that you use data Shapley to find the good data points. And these are examples of data points that get very high value. And as you can see, among this very cheap, non-clean data set, the ones that get high value are the ones that are actually very similar to your test data. There is another example, which is a very famous example in the field, and it's a very important one. So we know as a fact that face detection model, or in our specific case, gender detection models, are very accurate for white males, let's say. But for minorities, they're not that accurate, specifically Black females. So there's this very famous data set, Faces in the Wild, and let's say this is our training data. And there's this very small test data set called PPB, which is designed to be balanced among different skin colors and different genders. So you have equal distribution of white males, white females, and Black males and Black females. But in your training data, this very famous data set of W, it's actually mostly white men. So when you train a model on FW and test it on PPB, you see your performance drops because your model is biased towards white males. So it's not going to have a very good performance on Black females. But let's apply the same method. So this PPB data set has 800 images. We take 200 of them as the data set that we use for data valuation. We compute the value of the data points here, remove the ones with negative value, reweight the ones with positive value, and look at the model's performance on the remaining 600 images. And as you can see, the performance improves from around 84% to around 90%. So there is an improvement in performance, but most interestingly, when you look at data points that have high value, they are almost all women. And at the same time, there are women from minorities. So that's a very good sign that Data Shapley is actually picking up the type of data point that is useful for your target task. But this was Data Shapley. This is basically traditional game theory. So as we said, you have a fixed training data point, meaning that you have a fixed set of players. And you don't have any statistical assumption about these players. So you just think of, let's say you have a data set of 10,000 data points and there are just 10,000 players to you. You are not having literally any machine learning assumptions. But in machine learning, usually we assume data is coming from an underlying distribution. So let's say LFW data is coming from the underlying distribution of human faces. And the data points in it are somehow related to each other. They are not just unrelated individual players. And this has some implications. So the data Shapley value that we talked about is parameterized by your initial data set. Let's call it here S. So as we talked before, your training data set is assumed to be fully fixed. And this is a problem because what if you add or remove a data point from your data set? So let's say you have data set S and you compute the value for data points in S and you just go and buy one more data point Z prime. Given the data Shapley framework, you have to recompute every data point's value again because your game has changed. Now you have one more player and everything needs to be recomputed. And the other thing is, let's say you have this data point Z that you want to find a value for. And let's say this data point Z is in two different data sets, S1 and S2. But S1 and S2 are both coming from the same distribution. Using the data Shapley framework, you cannot say anything about how different the value of Z in these two different data sets is, because it's just for each of them you have to compute the value. Although S1 and S2 are very similar data sets coming from the same distribution. So these are the drawbacks of the data Shapley value. And it has some real world implications. It has some practical implications. So going back to our very initial simple example, assume you are a buyer of data and you have the seller of data. The way data Shapley framework works is that the seller has to first give you their data. So you get the data fully. Then you have to compute the data Shapley value. And then you have to return the value to the seller. And the seller has to trust you with the whole process of giving you the data and just believing any value you report back. And because of these reasons, you are usually not very willing to give your data before getting any value for it. And this is not very practical. But things get even worse when you have several buyers, because if you sell the same set of data points to different buyers, because they have a different initial training set, given the data Shapley framework, the value each of them is going to report is going to be different because they're just going to compute the data Shapley of the data points you sell based on their own initial data set. So all of this means that we need a more intrinsic measure of value, a more statistical measure of value that is not parameterized by a fixed data set S. So going back to our three ingredients of machine learning, we said we have three main pillars. So we have the training data, we have the learning algorithm, and we have the performance evaluation. Let's replace this training data, this fixed training data set with trained data distribution. So let's assume you have access to the underlying distribution where your data is coming from. For example, you have access to the underlying distribution of all the faces of humans. This changes the data Shapley framework to a framework which is a distributional Shapley value. So now you're talking about the distributional value of data. And because it's coming from a statistical notion, it is more tailored towards ML applications. Now, how can we define the distributional value of a data point Z? Let's say we had a fixed data set B where Z is a part of it. As we talked before, we have this data Shapley value formula that will compute the data point Z's value if it is in a data set B. But this time, instead of a fixed data set B, we have a data distribution D. So if we find the value of data point Z in all possible data sets of size M that come from distribution D, what we can do is just assume you have all the possible data sets of size M minus 1, you add Z to them, and you compute the data Shapley value of Z in that data set. We define distributional value to be expectation of all of these possible data Shapley values. So this data Shapley, this sampling M-1 data points from the data distribution, calling it B, and then finding the value of Z as a member of that data set. By definition, this data Shapley value is now a random variable, so it's not a fixed value anymore. The distributional Shapley is basically just the expected value of this random variable. This solves the problem of data Shapley value being dependent on a fixed data set. This time, there is no dependence on a fixed data set. You have a data distribution D, and you find the data point Z's value given this data distribution. So this time, everyone can agree on data point Z's value. Different buyers will not report different values. There's a different way of talking about or defining distributional Shapley value. So it's just similar to the data Shapley value formula that we talked about. Let's say S is a random subset of a random sample of your training data distribution. What is its size? How many data points does it have? It's again a random, a uniformly random value between 1 to n-1. So we sample k uniformly from 1 to n-1, and then we sample k data points from that underlying data distribution. Now you look at the performance of a model trained on this subset S. You add Z to it and look at the marginal performance. So this is literally the Lee-Van Oort score of data point Z for the specific subset S. The distributional value of data point Z is just an expectation over all the Lee-Van Oort scores it can get given your data distribution. So just as before, a data point Z that gets a very high value is one that is usually contributing to any possible subset of your data distribution, and vice versa. The good news is that when we talked about data Shapley value, we had three main properties in mind that it should satisfy. The good news is that distributional Shapley value satisfies statistical variance of those Shapley axioms, of those desirable properties. And just similar to the data Shapley value, we have developed efficient Monte Carlo approximation methods and heuristics to compute and approximate the distributional Shapley value. And as we said, we want a more intrinsic measure of value, and now we have a more intrinsic measure of value, and that is that the value does not depend on a fixed data set, it depends on the data distribution. But one good thing is that now the value has become a statistical notion, meaning that now when we talk about value, it's much closer to the notion of machine learning. And the good thing is that now we can apply existing machine learning knowledge to the concept of data value. And let's talk about one example. So let's say you have the data point star again, And you know its leave one out score with respect to the two other data points. You know its marginal contribution to data point hexagon and pentagon. Let's say we have another data point, faded star, which is just a small perturbation of data point star. So these two are very similar. Using the data Shapley framework, you cannot say anything about how different the value of these two should be, although intuitively expect the values to be very similar. But now using the idea of distributional Shapley value, you can actually say how close the value of these two can be. So the proposition is that if two data points are similar, their value should be similar. So data point star and faded star, they're very similar, and given this data distribution, they should get similar values. So the idea is defining a Lipschitz stability concept, this time for machine learning and for data value. And the idea is that, let's say we have some important metric space where you know the distance between z and z prime. The marginal contribution of data point z to subset S cannot be much different given that these two data points are close in that metric space. So let's say this is our metric space. Data point star and faded star are very close. So this distance is very small. The Lipschitz stability concept says that the marginal contribution, so this marginal contribution between these two should be very similar. But the question is that when does this notion actually apply? So what family of models actually satisfy this Lipschitz stability idea? What happens is that theoretically, we prove that for regularized empirical risk minimization and for the family of RKHS models, theoretically, the idea of Lipschitz stability exists. But experimentally, we show that Lipschitz stability exists in most of the machine learning models that we use, in most of the model classes. And what is the use case of this Lipschitz stability? Let's say I have a very big data set M, and I want to find the distributional value of every data point in this very large data set M. Now, what I can do is that randomly sample a small subset of data set M. And what happens is that if I have a large enough random subset of data set M, for every data point in M that is not in S, there is a data point. So let's say you have a data point Z in M that is not in S. You're going to have a data point Z prime that is in S and is very close to Z if subset S is large enough. So let's say I sample a random subset S that is large enough. I compute the distributional value of data points in S, which is the most computationally intensive part of data valuation. Now, for the rest of the data points that are not in S, I can literally interpolate the values of data points in S, because as we said, for any data point Z that is in M and not in S, there's a data point Z prime that is in S, for which we have computed the distributional Shapley value. Now, if I have a lot of these data point Z primes for a given data point Z, I can literally interpolate these values and this time predict the value of data points that are in M. So the problem from computing value literally transforms to a problem of inferring value. Now let's talk about approximations. As we said, we have developed efficient approximation methods for data value. So let's start with data Shapley. As we said, for data point K, its data Shapley value is its weighted average of its marginal contribution to different subsets S. we can literally rewrite this formula as the following. So let's say big pi is the set of all permutations of n data points that you have in your fixed training data set. So it's the size is n prime. There are n prime different possible permutations. We sample one random permutation from the set of all possible permutations of the data points. And we look at the subset of data points in your training data set, in the subset of that n data points that appears before k in that random permutation. As we see, the marginal contribution of k to that specific subset, its expected value would become the data Shapley value of k. So this results in the TMC-Shapley algorithm, truncated Monte Carlo approximation. So going back to our simple example, we have data point star, hexagon, and pentagon, and we sample a random permutation of these three data points. So you first get star, then hexagon, then pentagon. You start from scratch, so you have a model that has random prediction. Then you train a model on data point star and look at its marginal contribution to that. Then you train a model on data point star plus data point hexagon and see how much improvement you have. Then you train a model on three of them and you see how much improvement you have compared to just using star and hexagon. By going over this random permutation, training a new model, looking at its marginal difference, you are getting one sample of this expectation computation problem, one Monte Carlo sample. So if you repeat this algorithm, what happens is that you're going to get more and more Monte Carlo samples of each data point k's value. The truncated part, what it says is that, let's say instead of 3 data points, you have 1 million data points. For the first few data points, adding one data point is going to change this performance. So if this S pi k is very small, then adding data point k is going to change this performance metric. But after a large number of data points, let's say after having a million data points, adding one data point k to a million data points in S pi k is not going to change anything. So you can approximate the marginal contribution of k by 0. So you sample a permutation, you train a model starting from point 1, point 1 and 2, point 1 and 2 and 3. But when you see your performance saturate, so whenever adding one data point k to your subset does not change anything, you just truncate the computations. And that's why it's called truncated Monte Carlo. So I wanted to thank you all for your time, and hopefully I'll be present for the one-on-one session to answer the questions.
Okay. Thanks, Amirata, for his nice presentation. Hopefully, he's right now with us. So, yeah, I hear you well, and I hope you also hear us well. So we're waiting to see if attendants have any questions. Now, any questions yet? I'm just waiting. Okay. Yeah. Let's see if anybody has any questions. Not any questions yet. Okay, yeah, finally I received the questions. let's go to the question answer mode. Uh, okay, yeah. Aryan has asked, how is the implementation of the approach? Should we train the model each time for batch of data and adding data or removing it? I think take a long time to find bad data points in large data sets. I think his question is not complete, but anyway, can you
I
hear?
think I get the question. Yeah, it's
Okay.
actually a very, very good question. Probably the biggest challenge with computing data value. It's true that you need to train your model many times. So clearly you cannot use it for a very large deep neural network, although people have used it with some heuristic tricks. But it can be actually much faster than it seems. So basically, as we mentioned, you sample a shuffling of your data set. So let's say you have 1,000 data points and you shuffle them randomly. You train a model on data point 1, then on the first 2 data points, then on the first 3 data points, so on. But the good thing is that many of the machine learning models saturate after a few data points. So if you have a logistic regression model, if you train it with 100 data points or 101 data points, things don't change that much because already with 100 data points, the performance has saturated. So that's why this algorithm, the efficient algorithm we're computing it, is called a truncated Monte Carlo. So the Monte Carlo part is for the sampling and shuffling. The truncation is that once you have sampled a shuffling of your training data, you just do this training up to a very small subset of that shuffling and just truncate the computation there. So the number of model trainings is almost on the order of your training data set, not on the squared. If your data set is very large, it definitely is going to take a long time. But the good thing about it is that it's Monte Carlo sampling. So each of these permutations, each of these Monte Carlo samples can run in parallel. So what we did is that we used 1,000 CPUs, each of them just computing one of these shuffles, marginal contributions. And therefore, for most of the realistic models, you can actually practically do it. It's just that if you have medium level computational resources. There are also other tricks. We introduced this gradient Shapley heuristic in the paper that is curated towards neural network models. There is no theoretical justification for it, but it's very fast. So the answer is yes, it's computationally intensive, but it's manageable.
Thanks. So we go to the next question from Yusuf. He has asked, have you thought about formulating your problem in an information theoretic framework?
Oh, that's a very, very good question. So the answer to this question is worthy of a complete research work or a few research papers by itself. The main thing about it is that the data Shapley and distributional Shapley frameworks are model agnostic. So we talked about your learning algorithm can be any black box. If you want to run an information theoretic framework for data valuation, I would think it would be very difficult to do it in a model agnostic way. You should choose and fix a model first, and that's actually what is happening in the data valuation research right now. So the follow-up works that have been coming out in the past 6 months, they put the model agnostic kind of feature aside. They focus on just one model. So how to find data Shapley values very fast for this, let's say, specific logistic regression model or kernel density estimation model. I think in those scenarios, for some simple models, it should be very possible. It would be a very impactful research if someone's interested in doing so.
Okay, and the next question from Mahdi. He has asked, could Shapley theorem be used for features as well?
Interesting question. It has been used for features as well. So it was actually first applied for features. It's a very hot and very useful area of research. There are many, many papers. You can check, for instance, a method called SHAP, so SHAP by Lundberg et al. I think it was published 2017, if I'm not wrong, that used Shapley value for features, and they got very good answers for feature interpretability, feature importance scores. So yeah, people have done it before, and they are still doing a lot of research on this.
The next question from Puyan. He has asked, finding bad as well as inappropriate data is not hard for a model?
I kind of don't get a question. So if the question is it hard? On a computational sense, it takes a lot of computations to find a data point with low Shapley value. That's true. But the Shapley value framework is very model agnostic. So independent of your model, you can run this framework. It just depends on how much computational resources you have. And for any model we have tried, there's usually a percentage of your training data set that is negatively valued, or in other words, bad. So it is possible. It's not hard.
Thanks. And the next question from Hossein said, thanks for your presentation. You mentioned one use case of data value estimation in the domain adaptation setting by omitting some samples which are not relevant to the target domain. Now consider that we have a trained model and we cannot retrain or fine-tune it. How can we calculate the value of a new sample from a target domain to understand how much trust can we put to the trained model's prediction?
Okay, so that's a good point. The data Shapley framework, your data set is fixed, so you cannot compute value for a new data point. But the second half of the presentation, which was do you hear me?
Yeah, I hear you.
The second half of the presentation, which was distributional Shapley. The distributional Shapley, because it's in a statistical notion, it can generalize. So if you have a set of other data points that you have computed the value for, you can use those to kind of get a notion of how valuable your new data point is. But in general, if you're talking about a fixed model that cannot be retrained, the data Shapley framework cannot be used at least as is. So the general answer to the question is no.
Okay, thank you very much. And let's see if there's any other questions. No, there is no other question. Thank you very much, Amirata, for your time and for your nice presentation. And I hope we can also have you on our next events.
Sure. Thank you very much for your time.
Thank you. And
enjoy your day.
Bye. Okay, and so the first two talks are down now, and yeah, we'll go to the next talks. Actually, the session chair would be another person. And so, bye everyone, and have a nice day.